We're going to be looking at several demonstrations that have to do with center of mass and how the position of the center of mass of an object is related to the object's stability. Let's begin with a parlor trick that you've probably seen before. Take a fork and a spoon, interlock them, slip a match in between the tines of the fork and balance it on a glass, or in this case a beaker. And you can make the whole combination balance there. The reason that works is because the center of mass of the system of the fork and the spoon is actually right at the lip of the beaker where it's balanced. So the point of support is directly below the center of mass. The reason the center of mass is at that particular point, it's not actually within the fork or the spoon, it's somewhere here below it. Now, by symmetry, since the fork and the spoon are about the same shape, the center of mass is going to be along a line approximately here. But because the spoon extends way out and the fork extends way out, this will displace the center of mass downward. And so the center of mass of an object does not actually have to be physically within the object. Let's look at another example. Here we'll be using our two-dimensional NCSSM student. We'll call this 2D. And I'm going to put some weight on 2D's hands and balance 2D right there on the top of the head. It's very easy to balance. Now, like the fork and the spoon, we've got a lot of weight on the outside extending out away from the point of support. Because of the symmetry of the object, the center, we can know the center mass will fall on a vertical line right here below my finger. And it's going to be quite a ways down because most of the weight is here on the clamps. Now, this is a very stable object. So next we want to talk about why it is that this is stable and what the position of the center of mass has to do with that. I'll begin by looking at a different object where it might be a little bit easier to see what's going on. I'll just use this. This is a support for another piece of equipment. It has a wooden base and just a metal rod. Sitting like this, it's very stable. It's very hard to make this thing tip over. But if I put it like this, it's essentially impossible to keep it from tipping over. That has to do with what happens to the center of mass when the object tips. The center of mass of this object is inside the piece of wood. In order to tip the object, notice that the center of mass has to rise first. It's going to rise before it finally starts to fall over again. It has to rise quite a large distance. On the other hand, if the object is like this, the center of mass is now up here, and as the object starts to tip, the center of mass immediately begins going downward. So the difference is that if the center of mass has to be lifted, then the object is going to be more stable than if it just falls immediately. And the farther it has to be lifted, then the more stable the object will be. Now let's take a look at 2D one more time. The center of mass of 2D is way down here because that's where most of the weight is. So I would actually have to pull this to the side like so in order to raise the center of mass. And in fact, I couldn't even raise the center of mass far enough in order to make the object tip over completely. On the other hand, if I put most of the mass above like this, now the center of mass of 2D will be up here, it'll be above my finger, so as soon as I let go, the center of mass will fall immediately. And it would be impossible for me to balance without moving my finger, and even then it's very difficult. Now there are a number of toys that work on this principle. Here's one of them. This horseman has, the horseman is plastic, and there's a fairly heavy weight here on the end. So the center of mass is going to be down in here. Actually, the center of mass might be somewhere within the weight here on the end, or at least very near to it. We have no trouble balancing this on its platform. The center of mass is way down here below it. In order to make this thing tip over, we'd have to raise the center of mass above this point, and of course, that would be impossible without practically pushing it off of its stand. Here's another toy that works similarly. It's a bald-headed eagle, and this one can be balanced on its beak. Now, if you want to try this yourself and don't have toys like this at home, it's very simple. All you need is a pencil with an eraser and a paper clip. Open up the paper clip. Stick one end in the pencil eraser, and you can balance the other end on your finger. So the center mass will fall on a straight line directly below my finger. In this demonstration, we're going to see how to find the center of mass of an irregularly shaped object. For the object, we're going to use the state of North Carolina. In order to help with this, I'll be using this piece of equipment. There's a nut tied to a string with a pin tied on the end. What I'll be doing is using this string with this pin and a weight attached to it, together with the map, so that I can suspend the map from the pin and see where the string falls. So I'll begin by putting the pin here. This can be anywhere, but I'm just picking somewhere around Elizabeth City. I hold the end of the pin so that the map is suspended from my hand. So this means that the center of mass of the map will be somewhere along this vertical line. With a marker, I'll draw the line on there. It's kind of a rough line, but you get the idea. So we know the center of mass falls somewhere on that line, but we don't know where. In order to find out, we need to draw a second line to intersect with the first. So to do that, I'll put the pin in somewhere else, somewhere up here around Boone. Suspend it once more. Draw another line. And that's enough to find the center of mass, which should be the intersection of those two. But just for good measure, we'll do it one more time to see if the third line also passes through that point. So I'll put this somewhere down around Wilmington. And I don't have to draw the line for you to see that the string is passing very near that intersection point. So no matter where I put that pin, it should pass through that particular point. And let's see where that is. It turns out that it's very close to the city of Sanford. So if that really is the center of mass of North Carolina, then I should be able to balance the entire state on that particular point. Now, when I said that Sanford was the center of mass of the state of North Carolina, I was talking about this cutout of the state. Actually, the center of mass is influenced by the distribution of mass in the object. And for North Carolina, we know we have mountains to the west, and so that's going to increase the mass on the western end. And we have bodies of water distributed throughout the state in various places. So all of these will affect the actual center of mass of the state of North Carolina. We're going to be looking at the forces acting on an object in equilibrium. And the object is going to be this garbage gobbler truck on this inclined plane. The plane is inclined at an angle of 30 degrees with the horizontal. There's also a bumper back here which keeps the truck from falling backwards. Now these strings and these pulleys, we're going to find out later what they're for, but for now we're just going to ignore those. Let's take a close look at the forces that are acting on the truck in this situation. First, we know that because it's in equilibrium, that the forces acting on it add up to zero. There are three forces. Those forces are the weight of the truck downward, pointing to the center of the earth. The bumper exerts a force parallel to the plane, pointed like this. And the plane exerts a force perpendicular to the plane, like this. That's a normal force. those three forces add up to 0. Now let's take a closer look at those forces and how they depend upon the angle of the plane. And for that I'm going to use this setup because it's a little bit smaller and I can move it around. So here's the bumper, and here's the plane, and here's the car instead of the truck. In this situation where the plane is horizontal, we don't need the bumper force to keep the car there. I can put the car anywhere that I want to and it will stay. So we just have two forces, the normal force of the plane up, the weight force down. Those two forces are equal and opposite. Now I'm going to tilt the plane up more and more and more to get us up to a vertical angle for the plane, or a 90-degree angle. And you can see when I approach 90 that plane is not exerting any force on the car anymore. All the force is being exerted by the bumper. There's a bumper force up and then the weight force down. And so now those two forces are equal and opposite to each other. Well, for any angle in between, there will be both a bumper force and a plane force, a normal force from the plane. But those two forces will depend upon the angle. So we're going to see in the segment that follows exactly how those forces depend upon the angle of the plane. We'll begin, like always, by representing the object, the truck, by a point. There are three forces acting on the truck. The weight of the truck, which acts vertically downward, that's mg. The normal force, which acts perpendicular to the plane and away from it, that's n. And the force of the bumper, which acts parallel to the plane and upward along the plane, we'll call that F. We need to set up x and y axes. It's convenient for that purpose to set up an x-axis parallel to the plane. We'll have plus x pointed upward along the plane, and a y-axis perpendicular to the plane. We'll have the plus y-axis pointed upward away from the plane. Now we need to look at the components of the weight force along the x and y axes. Those will be along the y-axis, this component, along the x-axis, this component. To determine what those components are, we need to know this angle. And in order to obtain that angle, we can relate it to the angle that the plane makes with the horizontal. Call that theta. In order to make the relationship, I'm going to extend a couple of lines. I'll extend the y-axis until it crosses the ground. I'll extend the weight force until it does the same thing. Now let's look at a couple of angles. The two angles are the angle of the plane with the horizontal and the angle of the weight force with the y-axis. Notice that both sides of those two angles are perpendicular to each other. The weight force is perpendicular to the ground, and the y-axis is perpendicular to the plane. There's a theorem from geometry that states if two angles have their corresponding sides perpendicular, those angles are either equal or supplementary. In this case, we can see that they are equal. So that means that the angle we're interested in is the same as the angle theta. Knowing that, we can then write that the component of the weight force along the y-axis is the side adjacent to our angle theta, and therefore it is mg cosine theta. And the component of mg down the plane is the side opposite the angle theta, and that is mg sine theta. Now both of those components are in the negative direction. mg cosine theta is in the negative y direction, so I'll put a minus sign in front of it. mg sine theta is in the negative x direction, so I'll put a negative in front of it. Now we're ready to write the net force equations. The net force along the x-axis is composed of two forces, F, which is positive, and minus mg sine theta. And the net force along the y-axis, also composed of two forces, and those are N, which is a positive force, and mg cosine theta, which is negative. So that gives us two net force equations that we can use to complete the analysis of this situation. Now that you've seen the equations for the forces, we're going to take some measurements so that you can do some calculations. In order to do that, I'm going to replace the normal force of the plane and the bumper force with two other forces. I'm going to replace the force of the bumper with a tension force exerted by this string. And I'll do that by putting the string over the pulley here and hanging a weight on the end of the string. I'm not going to do that now. I just wanted you to see it. And notice that the string is pretty nearly parallel to the plane. And I do that because the bumper force is also acting parallel to the plane. Now, in order to replace the normal force, that force is perpendicular to the plane. This string will replace the normal force of the plane, and notice that it's perpendicular to the plane, just like the normal force would be. And I'll drape it over a pulley, and I'll put a weight on this side. Now, if we knew the mass of the truck, then we could calculate what those two weights on the side had to be, hanging over the pulleys, in order to replace the normal force of the plane and the bumper force. Now, I know what the mass is, and so I already know what those weights are. I'm going to have you work backwards, though. I'm going to put the weights on there. I'm going to tell you what they are, and then your job will be to use the equations for the forces to calculate what the mass of the truck is. So I'm going to put those on right now. This particular mass is a total of 0.265, or rather 0.270 kilograms. Now that's a mass, and we're interested in a weight because that's a force, and that is what provides us the tension force in the string here. So you'll need to convert that mass into a weight using the acceleration due to gravity. On this side, there's a total mass of 0.465 kilograms. And when I hang that on there, notice that the truck moves ever so slightly. You can see that the planes are not needed anymore to support it. I'm going to pull them away. And also the bumper is not needed either. And so the truck hangs there in the same orientation as if it were on the plane. But we've simply replaced the bumper force with the tension force of this string and the normal force of the plane with the tension force of this string. Your job now is to take the two measurements that I've given you and the equations that you have and calculate the mass of the truck. And then you'll come back and take another look at the video and find out, we'll measure the mass on